The next theorem that I call theorem Q, it's not a numbered theorem, but Q being for the rational numbers, states that the set of rational numbers is countable, which is pretty amazing to think about. Well, because of some of the theorems and corollaries that we've already proven, this proof isn't too bad. I do need to come up with a function. Actually, before I even write the proof, let's recall what the definition of the rational numbers is. Recall that Q, I'm going to write it slightly different this time, is equal to the set of all A over B, such that A and B are both integers. I'm going to require that, instead of saying B less than 0, B not equal to 0, I'm going to require that B be greater than 0, which is fine. Yes, it can be negative in general, but we can get the negative number, the negative rational number, by just forcing A to be negative. So we can say that A can be any integer at all, and B we're forcing to be a positive or a natural number. We're also going to force A and B to be relatively prime. All that means is when we write the rational number as a fraction, we're writing it only in its reduced form. So 1 over 2 will be one of the elements of this set, but 2 over 4, although equivalent to 1 over 2, won't even be listed in this set. So each rational number will have a unique representation. And lastly, if A is equal to 0, then we're going to force B to be 1. So the only way to write the number 0 would be 0 over 1. This gives us, again, every rational number has exactly one representation in this set, one and only one. So it's simply an alternate definition. It is exactly the same set as the other way we defined it, but we're requiring that this contains only unique ways to write each rational number. And here's how the proof goes, that the rational numbers are countable. Let's let the function f that maps the rationals into z. I'm going to create this function. We don't know that it exists just yet. Be defined as follows. All right, so for every q, every rational number in the set of rational numbers, where q is equal to a over b in the unique representation, as described in this set here. So essentially, b is a positive number, a is any integer, and it is in reduced form. Okay, for that, we're defining f of that q, which is equal to f of a over b, because q is equal to a over b, is equal to this. That ordered pair. We're mapping each rational number into its ordered pair, where a is the numerator, could be any integer, and b is the denominator. It is strictly positive. And this one other way, just to make sure there's only one way to write 0. If a is 0, then b is a 1. All right, the function, this function f, is 1-to-1 from q, I'll say onto a subset, which means I could have written just into, onto a subset of z cross the natural numbers. Remember, a can be any integer, b can be any natural number. integer crossed with natural number. By theorem 0.16, z cross n is countable. Remember, this is a countable set, this is a countable set. The cross product of two countable sets is also countable. And in parentheses, I'm going to write in any subset of z cross n is also countable. And that was by the corollary, yes, corollary 0.15. And the last sentence, therefore, since S is equivalent, S, what I mean by that is Q. Since the rational numbers, the set of rational numbers, Q, write that, is equivalent to a subset of z cross n, that countable set. Since that is true, Q is countable.